Good morning, POE. Today we're going to go over the introduction to structural member properties. Now, I have a link to some similar information that you will find in this PowerPoint. The link that is on this schedule that I sent out and it is on Canvas under schedule now has a link to the electronic textbook on mypltw.org, but it is not in a PowerPoint format. So I have this PowerPoint format and a PDF version of this PowerPoint saved under Modules, Unit 2.1 on Canvas. So if you go to Modules on Canvas under Unit 2.1, you can either open the PowerPoint version, which is the best way to open it, or the PDF version if you do not have Microsoft at home. Okay, so let's get started today with our PowerPoint. I'm going to go back and forth between the PowerPoint and Smart Notebook so I can draw some things and talk about some things in the PowerPoint. So let's start with the PowerPoint. Okay, all right. So structural member properties, moment of inertia, known as capital I. So let's start with looking at our formula packet. If you turn your formula packet to page 5, and page 5 at the top should say 10.0 section properties. And immediately under that, you see on the upper left-hand corner in a box, moment of inertia. And the formula says capital I, little x, so sub x, equals B, which is base, h, height, cubed, divided by 12. So base times height cubed divided by 12. The key to that formula, if you're going to type it all in your calculator at one time, is to remember that height is cubed first, then multiplied times base, and then divided by 12. Remember your order of operations. Please excuse my dear Aunt Sally, right? Parentheses, exponents, then multiplication, division, etc. So make sure you do the height cubed times the base divided by 12 to get this answer. Okay, so let's go back to our PowerPoint. Moment of inertia is a mathematical property of a cross-section measured in inches to the fourth that gives important information about how that cross-sectional area is distributed about a centroidal axis. Now, we have not done centroids yet. We will be doing it soon, as you can see on our schedule. But basically, the centroid is kind of like the center of gravity, right? It's the balance point of anything. So it's the balance point of your pencil. It's the balance point of a beam or a piece of wood or a piece of metal. It's where we could support it, and if we supported it there, it would balance. Okay? Stiffness of an object related to its shape. Okay? So stiffness of an object related to its shape. In general, a high moment of inertia is a greater resistance to deformation. So if I were going to write notes on this in my engineer's notebook, I would definitely focus on this sentence. And in simple terms, what it means is when we do this calculation for I, if the number is high, it means that that material does not bend easily, right? A high moment of inertia is more resistant to deforming or to changing shape or, right, to bending. So the higher the number is when we calculate it, then the better it is at being deformed. So here's an example of two boards, okay? This board is a Douglas fir, so board A is a Douglas fir. Douglas fir is a type of tree. When you buy a Christmas tree, that's one of the types of Christmas trees you can buy, is Douglas fir. So this is wood from a Douglas fir tree. And A is 8 feet in length, okay? It says it is 1.5 inches by 5.5 inches. So that basically means If I go back to SMART, okay, so for SMART, okay, if I were looking at this board from the end, okay, it means that it is 1.5 inches wide and 5.5 inches tall. Okay, so it is 1.5 by 5.5. And how do I know that? Is because if I go back and I look at the actual picture of it, right, the bottom here is 1.5. That's obviously smaller, and the 5.5 tall. So on this picture, we would say that base equals 1.5 and height equals 5.5. Okay, and then on the other one, so this is called joist orientation. This is a board being used as a joist orientation, meaning it's standing upright like that. A plank is here, and a plank is when we use the board flat. So, for example, if you have a deck at home, all of the boards on top of your deck look like this. They're laying flat like this. And those boards are in plank formation, right? So you've heard of walk the plank. Well, that's kind of the same thing, right? It's like a diving board, so it's wide and flat and not very thick. So that's plank. Joist is what holds up your deck, for example. So if you look underneath of your deck, you'll see a whole bunch of boards that are like this, standing up like this, and those are called joists, and they are in a joist formation up on their edge like that. Plank formation. So here it says that board B, is 8 feet long also, 5.5 inches by 1.5 inches. So if I were drawing that one out, I could say, okay, so B, so let's go back up, right? So this would be A, and B would be like this. And that would be 5.5 inches and 1.5 inches. And here, my base, so the base of my board is 5.5, right? And the height is 1.5 when I look at it from the end, okay? So when we want to calculate the moment of inertia, we're going to do base times the height cubed. So I would do 1.5 cubed times 5.5 divided by 12. If I were using this board, base times height cubed, so cube the height, 5.5 cubed, times the base divided by 12. Okay, and remember, the higher the answer, then the higher the moment of inertia, and then the higher or the better it is at resisting deforming or bending or changing shape when under force. Okay, so if we go to the next slide here, okay, it says what distinguishes beam A from beam B? Will beam A or beam B have a greater resistance to bending? Okay, so the way we would find that, right, is we would calculate I for both of them. And the one that has the higher answer is going to resist deforming, resist bending. The yellow arrow just represents the fact that something is pushing down on it there. Okay, so if something pushes down on this one here, how much will it bend? Right? Or how much will it resist bending? And if something pushes down on this one here, then how much will it resist bending? And this is basically what it would look like. So this one, you can tell, wow, that's really strong. It's not bending at all. There's no green, there's no yellow. You can see just barely here that it's moving just barely, right? Whereas this one is changing colors, it's bending a whole bunch, and is, so if I had to guess, I would probably say that this one, if I do the math, has a higher moment of inertia, and that this one has a lower moment of inertia. Because remember, higher moment of inertia means it's higher, like it is better at resisting deforming. This one has a lower moment of inertia. It is not as good at resisting deforming. Okay? So why did beam B have a greater deformation than beam A? difference in moment of inertia due to the orientation of the beam. So orientation is just like how it was sitting, how it was being used, right? And this was the one that I showed you. It was A of the one that I showed you, right? So A, it had 1.5 base and 5.5 height. So if we do the moment of inertia, base height, so 1.5, 5.5 cubed divided by 12, make sure in your calculator, notice they did 5.5 cubed. That gets done first, right here, times base. So height cubed times base divided by 12. And you get a moment of inertia of about, let me back up, 21 inches to the 4th power. So sorry about that. The numerator was about 250 divided by 12, which is about 21. So let me go back. That was my mistake. Sorry about that. Okay. So it is really about 21 inches to the 4th. Okay, that's really okay. And if we go back to the other one, we can see, so this is beam B, right? It has a base of 5.5 inches, a height of 1.5 inches. So 5.5 inches, the height, we're going to cube. So 1.5 cubed is 3.375 times 5.5 divided by 12 equals about 18.5 divided by 12, which equals about 1.5 inches to the 4th. Okay, so this was 1.5 inches to the 4th. And remember, higher moment of inertia equals better at resisting deforming. So A is better at resisting deforming, which is exactly what we saw here. A is better at resisting deforming. So this has a moment of inertia of 21 inches to the 4th power. This one has one of 1.5. So this is about like 15 times better at resisting deforming than this one. Okay, so that's one part of this. Now the other thing we can calculate is how much does it actually bend? Oh, I was close. 14 times stiffer. So basically 21 divided by 1.5 is about 14. Oh, it is 14. Okay. So here, I'm not going to get into the math really big on how to do this, but we could basically break this into 3 shapes. Okay, so when we do area, if you recall, when we do area, it's length times width. So here we have 2.5 times 4, we get 10 inches squared. Here we do 2.5 times 1.5, plus 2.5 times 1.5 plus, right, 0.385 times 6.5. This would be 6.5. So basically we get an area of 10. And then here we have a giant big piece of wood. So this giant, imagine this wasn't cut out here. This is what it would look like, and it has a moment of inertia of 23.8. But the interesting thing is, it has an area of 23.8. So here's the interesting thing though. The moment of inertia here is 13.3. Okay, remember, the higher the moment of inertia, the better it is at resisting deforming. This one has a moment of inertia of 130. It has an area of 10. So look, this has the same amount of area, this, and this, as this piece. But because of how I've used it, look how much stronger, look how much higher the moment of inertia is. It's like 10 times better than this one. So this shape, if I were to push down on this and push down on this shape would be 10 times stronger. This one, right, is kind of like this shape, but as a solid block of wood. So if I took this, and this is kind of if we looked at it from the end, kind of like the drawings I did on Smart. This one, if I push down on it up here, right, it has a moment of inertia of 178. You'd be like, okay, so this is the strongest piece. Well, that's true. By itself, this is going to be the strongest, right? It's going to resist bending more than any of these because it's higher than these. But let's look at that. It has an area that is more than twice of this. So what happens if I took two of these pieces and put them next to each other? It would have an area of 20 inches squared, which is less than this one, and it would have double this. It would have 260 would be the moment of inertia. So if I took two of these and put them next to each other, they would be much, much stronger than this shape by itself and would also have less area. So it would be less material, it'd be lighter pieces, it would have less area, and it would be much stronger because it would be 260, much stronger than this. Okay. So then we talk about modulus of elasticity. So the modulus of elasticity says it's a ratio, okay, of some stress and some strain. So let's talk about that. Stress is how much force something is under. Okay, stress is how much force something is under. Strain is how much something is stretched. Okay, so stress is how much force something is under, and strain is how much stretching or change in shape that force causes. Okay, and that is called the modulus of elasticity. For your purposes, modulus of elasticity is going to be given to you. So E is going to be given to you in that equation. This is a key note to take. In general, a higher modulus of elasticity produces a greater resistance to deforming. So let's talk about that. So far, we know that a higher moment of inertia, high I, right? I was modulus of a moment of inertia. Capital I was moment of inertia. A high I means it can resist deforming. This is saying that a high E, a high modulus of elasticity, also helps it resist deforming. So a high I or a high E helps it, is an indicator that that material is going to be really good at resisting deforming when we push down on it or put force on it. So let's talk about two types here, okay? So here we have two different pieces of material. This one is a board. It's Douglas fir again. It's 8 feet long. It's 1.5 inches wide. So the base is 1.5 inches wide. The height is 5.5 inches tall. And it's giving you the area. Okay, so 1.5 times 5.5 is 8.25, right? Base times height is area. Okay, so far we have length, we have area. They're giving us moment of inertia, but we could have calculated that, right? We could have done base times height cubed divided by 12, and we would have gotten 20.8. And then B is ABS plastic. So some of you might have a deck at home, and it's called like Trek deck. It's basically plastic on top instead of wood, and it's made of this material, ABS plastic. And notice it is the same length, the same base, the same height, the same moment of inertia. Because remember, moment of inertia is based on base and height cubed divided by 12. And they have the same base, the same height. So if I cube this height, multiply it times the base, and divide by 12, I get this. If I cube this height, multiply it times the base, and divide by 12, I get the same thing. So at first, they seem like they would both resist the same amount. Okay, so this says which one will have a greater resistance to bending. Well, currently, if we just went with moment of inertia, we're like, they're equal. They're both 20.5, right? Or 20.8. 20.8. So they're showing you here that actually that plastic bends a whole lot more than the wood. So how do we know that? Okay. So it says the difference in the material modulus of elasticity. So in other words, these materials have a different E, a different modulus of elasticity. One of them has a higher modulus of elasticity. Characteristics of objects that affect deflection. So this triangle in science and math, delta, this is delta, just stands for change. So maximum change. So how much will this change? Okay, when I put force on it. All right, so here, notice that they are graphing it for you. So we have a support here. We have something holding it up. Here's our beam. Here's something holding it up. And then we're pushing down on it. We're pushing down on it with 250 pounds of force, right? Pushing down on it. And notice that L is the distance between the supports. So this is 8 feet from here to here. If this board were 10 feet long, let's say it was overhanging here by a foot and overhanging here by a foot, and they told us, hey, from the end to the end is 10 feet, but from here to here is 8 feet. If they told us that, we would still use the 8 feet because the L in the equation, okay, take notes on this, the L in the equation refers to the length between the supports. Does not include any length that might be hanging off the end. So L should always be the length between where it's being supported, not the overall length if they're different. Here, they're the same. The overall length is 8, and they're being supported on the ends. Now, what you will notice in these equations, so take notes on this, please. Length must always be converted to inches. Length must always be converted to inches. So you're going to see 8 feet in a second converted to 96 because they've converted it to inches. So moment of inertia. They gave it to us on this slide. They gave it to us, 20.8, but we could have found it ourselves, right? If they didn't give it to us, we could have found it because we would have done height cubed times base divided by 12, and we would have found it. But they gave it to us in this chart, and they're saying, hey, that Douglas fir has an 8-foot length, has a moment of inertia here. E, the modulus of elasticity, so E for our equation, they're giving us. This is given. This did not have to be calculated. This was given. This did not have to be calculated. This is being given and does not have to be calculated. Okay? So we have force is going to be 250. Length cubed. The length is going to be 96 inches cubed. So 96 cubed times 250. Right? 96 inches. So we're going to convert length, 8 feet, length, to inches. 12 times 8 is 96. 96 cubed times 250 divided by 48 times this given amount times moment of inertia. So for this wooden board, to calculate beam deflection, so beam deflection, I'll tell you in 1 second. So beam deflection is sounds like a complicated term, and this is all it means. Okay, if we have that support and we have this support, and then we take a board and we go all the way across and we lean it on there, and then we say, okay, well, let's put a force on it, right? Then really what's going to happen is that board is going to bend. So that board could bend like this, right? It could bend like this. So deformation is how much is the distance from here to here. How much did it bend? How much did it change, right? So delta max, whoa, that's a bad triangle. Delta max is the maximum amount of deformation, or bend in this case, right? It's bending, okay? All right, so we do the math. Notice they have 96 inches cubed times 250 pounds. So length was converted to inches cubed times 250. 48 times E. E was given 1.8 million or 1,800,000 times I. Right, and we have I. We could have calculated I, but they gave it to us. So we're basically saying that this board is going to bend in the middle 0.12 inches. Now the plastic piece, okay, still 250 pounds force, still length cubed, still 48. 48 is a constant, meaning it's a given. If you look at that formula, okay, so it's force times length cubed divided by 48 EI. So force times length cubed, so we'll cube the length first, times force. Modulus of elasticity was given to us, so we plug that in. Moment of inertia was given to us. Remember, we could have calculated that, but they gave it to us. And it has a 0.53 inches bend. So the wood is going to bend 0.12 inches when 250 pounds of force pushes on it, right? But it has a high moment of inertia. So remember, high E means high resistance to bending. Well, high, look, that's much higher than 419,000. 1.8 million is much higher than 419,000. So the wood should resist bending much more. Okay? And this will bend 0.53 inches. Okay? So the wood will bend 0.12 inches and the plastic will bend 0.53 inches. Okay, so before we go further, let me just find that formula for you because I know it is on the formula packet. I see it. Okay, so it's on page 5 still. I forgot where it was. And under 12.0 structural analysis, you see beam formulas. And in that very top beam, okay, where it says deflection, it says delta max equals P times L cubed divided by 48 EI. Just make the P an F, F as in Frank, F on your formula packet. Okay, anywhere you see P on your formula packet, just put an F as in Frank. Okay, so it's on the same property page under 12.0 structural analysis, under the next to the first picture of the beam where it says deflection, it says delta max equals P, change that P to an F, F as in Frank, L cubed divided by 48 EI. Okay, I'm going to pause there for today, and I'll be available to answer questions if you have them.